Hi, everyone. I'm Adele Newton. I am the Executive Director of CSCAN InfoCan. I'd like to welcome you to today's webinar, which is being given by our speaker, James Cordy from Queen's University. The webinar will be recorded and made available along with Jim's slides on our website next week. All of the attendees are muted and will remain so. If you have questions for Jim, please put them in the chat. Anything that we're not able to answer today because of time, I will work with Jim to get answers if we can. If you put them in the chat is recorded, so we'll be able to go back to it for reference. So without further ado, I am going to stop my video and turn it over to Jim.
All right. Hi, everybody. I'm really happy to have this opportunity. Let me just put my slides up to begin. Yeah. So when I was asked to give a webinar, I guess, as part of my Lifetime Achievement Award, I thought, well, I could talk about the research. I could talk about my career and all of the work we've done, and it would be traditional, I suppose, to outline that or to review it or something. And so started out and said, okay, I'm going to tell them all about software engineering by source transformation. But let's face it, software engineering talks are arguably the most boring thing on the planet, and I've attended hundreds of them myself. And unless you're actually right up the alley of the particular topic, it's not going to be very interesting. And this is a wide audience, so that makes no sense at all. So instead, I decided not to tell you about the research, but rather I'm going to tell you how the research came to be. So I'm going to tell you a story. My PhD supervisor, Rick Holt, always told me that writing papers was all about telling a story anyway, and I've always lived by that. So the idea of telling a story is familiar to me, and this one I thought was kind of cute, particularly for early researchers or for students to hear, because it involves failures and what happens and things like that. So I'm going to tell you the story of the particular idea and how it came to be that really made my career. This is the first webinar, I guess, from anyone getting this year's Lifetime Achievement Award. And I'm really happy to do that. I would have liked to put up a picture of the Lifetime Achievement Award, but the Lifetime Achievement Award itself actually turns out to be a crystal thing. And I do not have the appropriate photographic studio at home to actually make a picture of it. So I decided to draw one, and this is more or less what it looks like. Imagine that it's crystal and that it has highlights that are in gold and stuff like that. Anyway, I am really, really pleased to receive this award and somewhat surprised, but in particular, I'm deeply humbled. This award is important. It's important to our community. It's important to Canada. I'm even more humbled to be in the same group that includes Hugh Williams and Laurie Hendren, Wes Graham, and Morven Gentleman. I don't know Hugh, but I know his work, and it really is an impressive body. I know Laurie very well from her time as a student at Queen's and the rest of her career. And to be honored with someone of her stature in the international compilers and programming language community with her contributions is remarkable. It's horrible that we've lost her so early, and I really deeply miss her. And of course, both Wes and Morven were already, in my mind at least, legends in computer science when I was a student. So it's very humbling to be mentioned in the same breath as their names.
Jim, I'm sorry to interrupt. We seem to be having a problem with with just seeing your screen. I see it, but apparently the attendees cannot. Oh, here we have someone who can see it. So yes, some people can see it. There we go. So I'm sorry to interrupt. For those of you who can't see it, I apologize. And there we go. I apologize, Jim. Go on. Sorry.
Do we know why they can't see it?
No, it's on. So I don't know, for the people who aren't able to see it, perhaps go off and log off and log back in again. But a lot of people are letting me know that they can see it. So it seems to be not with the system at all.
All right, shall I continue?
Yes, I'm sorry.
It's okay. Where was I? Yeah. So obviously, I'm deeply honored to be mentioned with these other people, but also I was looking through the other winners from previous years of this award, and that's when my humility goes right through the floor. It's a remarkable crowd of people. All right, let's begin then on my story. So in particular, I began my career as the student of Rick Holt, who himself is or was a winner of the Lifetime Achievement Award, and deservedly so. A couple of years ago, we lost Rick a year and a half ago or so now, unfortunately. So I'm unhappy that he can't be here to hear me speak. Because one of the things I'm going to do is I'm going to thank him for setting me off on a career. And among the many things that Rick taught me early in my career was he said that the secret to research success is finding good students, pointing them in a good direction, and staying the heck out of the way. And in my experience, that's exactly how it works. It's remarkable what our students do for us, and they really do make your career. And staying out of the way is really the trick of it all. As a student, I was lucky to start with Rick. This particular picture is a picture from the launching of the Turing programming language, which we designed and implemented together in the first couple of years, actually, of my academic career after I graduated as a student. And it was around that time that the story I'm going to tell you starts. So the Turing language had been pretty successful already. It appeared on the front page. Our article appeared as the front page one in the Communications of the ACM in 1988, I think, approximately. And I was giving talks around the world about Turing and about teaching using it, and computer science education was really my research area. And my particular part of it was I worked on the design of the language with Rick and on the implementation of the language. So I supervised the compiler projects and the interpreter project that brought Turing to reality and to students. Turing is actually still around. It's still taught in a number of high schools in Ontario, and every year we still meet some students at Queen's who were taught as Turing as their first language. So I'm very proud of that system, and it's wonderful that it's been as successful as it has. So I was very proud of that work even back then in the late 80s, mid 80s rather. And one of the things that Rick did, and one of the places where I got to talk about Turing, was at IFIP Working Group 2.4. Rick introduced me to this gentleman, Professor Gerhard Goos of the University of Karlsruhe at that time, who was the chairman of IFIP Working Group 2.4, which is a working group on system implementation languages. And I proudly went to my first Working Group 2.4 meeting and presented what we had been doing on Turing and how successful it was being with students and how it was designed and how it was implemented and so on. And at the end of my talk, Gerhard stood up and he said, "Why is a talented young person like you wasting his time on these old ideas?" Now, of course, Turing was designed not to be anything new. It was designed to allow us to teach what was the best of what was known in programming languages at the time, which was something Pascal-ish. And I was taken aback by this. But I was even more taken aback when he said it in his characteristic way, which is, "Why is a talented young person like you wasting his time on these old ideas?" Well, I was crestfallen, absolutely heartbroken, and thought, well, what in the world can I do about this? I'm wasting my time. I'm wasting my time on these old ideas. I should be doing something new. So I returned home and began to think about what he had said. And I took it very seriously. At first I was insulted, but then I realized that in some ways he was right. I was doing things that were known and that were extensions to existing work. What would happen if I were to look ahead instead? And so, being a child of the 60s, well, a teenager in the 60s, I went back and looked at the influences on my life, and I ran across this quote from Bobby Kennedy. He said, "Some men dream of things that are and ask why. I dream of things that never were and ask why not." And I took that as an opportunity, that quote, as a direction, as an opportunity to think about what might be. And I'd started to look around at what we had been doing in the old ways, as Professor Ghost pointed out. I began to think about what would happen if we took away the limitations and said, why aren't we doing what we would really like rather than what we know how to do already? So now I'm going to show you a little bit about how the Turing language was designed. So this is an entire Turing program. It outputs high. It's the Hello World program, of course. And when we were designing the language, we would propose new features or new syntax or new semantics or new ways to say things that we thought were convenient and simple and easy to learn, which was the purpose of the language. But in order to try that out and give it to students and others and let them try this out, what we would have to do in those days is we would have to change the compiler for the language. So compilers have several parts. They have a parser and they have a semantic analyzer and they have a code generator, and then the code gets compiled or assembled into a machine code, and then you get to run it. And even for a simple new feature like this, something that was different from what we already had in other languages, we had to do work on the scanner screener, we had to do work on the parser, we had to do work on semantic analysis for sure, and we had to do some work on code generation to cause this to happen. So if you imagine I have a new set of language features I want to try out, and I want to see experimentally, is this good for teaching? Do students respond to this? I would have to make a new compiler out of an old one, admittedly, but it would take a month or so to make a new version of the language. Now, of course, the way we understood the language, because it was not introducing fundamentally new things, rather than wrapping up what we knew and making it easier to learn, the way we thought about it is we would propose a new feature or a new syntax or a new way of saying things that was simpler. And then we would say, okay, so what does it mean? And what we would do is we would, on a blackboard at that time, we would write down the feature we had in mind and how we would say it, so put high. And then we would put an arrow, and on the other side of the blackboard, we'd put what it means in an existing language. In this case, the existing language is PL1. or the SPK dialect of PL1. And what you see on the right is what the thing on the left in Turing means in PL1. It means it's a program. It means it should output a new line containing the word hi. And the other stuff is just required syntax in PL1. It was what we were trying to get rid of. We said, why do you have to say all that stuff? I have to say to my students, geez, you have to write P colon procedure options main semicolon. And they said, why do you have to write that? You just do. It's a program. And that's the kind of thing we were trying to get rid of. The important thing is that blue arrow. The blue arrow there means that this, the thing on the left, means that, the thing on the right. And that's the way we thought about it. And taking Bobby Kennedy's advice into account, I said to myself, okay, so why, if that's how we understand it, why don't we just write that? Why don't I just say this means that? And then in 5 minutes, I could have a working version of the feature on the left, introduce it to students and others, and have them run it. How could they run it? Well, we would translate automatically from the stuff on the left to the stuff on the right. The stuff on the right would get compiled in the language it's in and run, and presto, we can try it out. This allows a lot of experimentation in language syntax and semantics and design, and that's what I had in mind. So why not? Well, the answer was that there weren't systems to do that, and that actually doing that kind of thing was pretty tricky, in particular doing it in general, so not for put hi, but for any variant of the put statement in Turing. So I took this idea, and taking Rick's advice, I gave it to a very talented young student, one of my first graduate students, Charlie Halpern, who you see here. Charlie's a character, and that picture is pretty well representative of how I think of Charlie. Anyway, so Charlie and I discussed how this might be done. I had a background in compilers and in programming languages. Charlie had a background in artificial intelligence as an undergraduate. And he proposed a way to write this like so, where we basically have a first half, which is a pattern, so put expression. And he and I developed a notation to say generalization. So the red stuff is general. And then we say, okay, replace that by that. So in other words, the replace by represents the blue arrow you see above. And we made a programming language called TXL that could express pattern replacement pairs like this. And very quickly, we were able to use this idea to try out things. So we could start experimenting with new language designs and new language features. And we did some in numerical analysis and other extensions to Turing, and tried implementing them in TXL. At that time, computers were not very fast, maybe 1 megahertz. And it took a long time for our prototype of this idea to actually run. And so, for example, among the first things we tried to programs we tried to transform in this way, we were talking about 10 minutes to do something 20 lines long, and talking about many hours if it were, say, a couple hundred lines long. But it was possible to do it. And our prediction was, let's look to the future. 20 years from now, computers will be fast enough that this will happen in a short time, and we'll be able to use it to do practical sized things. So we put together this thing called TXL, and we decided it was a great idea and people would like it. And we thought, oh boy, we're going to publish this work. So we submitted this paper about TXL to one of the biggest and most important conferences in software engineering. And we received the following response. Among the other negative reviews, the following one appeared. This paper cannot be accepted because the system it describes is obviously impossible. Well, on the one hand, that was good. It meant we were looking ahead to places where other people were not thinking. On the other hand, it meant that we really, at that time, couldn't publish our work because nobody really wanted to believe it. And of course, once again, I was crestfallen. So we've developed a new idea. We've looked into the future. We're trying something new, as Dr. Gose had proposed we do. But nobody would go for it because they didn't know what it was, they didn't know what it did, and they didn't believe it anyway. Well, what does one do? Well, some people said the right thing to do would be, okay, move on to another idea and move and continue. And I know people, students and young professors who've done that with great ideas, who said, okay, nobody's accepting this, I have to do something else. But I'm a stubborn guy. And I decided that we should continue. But how? Well, an interesting thing I ran across was a quote from Dr. Howard Aiken, early computer scientist, who said, "Don't worry about anyone else stealing your ideas, because if they're any good at all, you're going to have to ram them down everyone's throat." In other words, if you've got a good idea, you shouldn't be too surprised that people won't accept it. Indeed, if it's really good, indeed, you will have to ram it down everyone's throat. So the question is, how do you ram a good idea like this one down everyone's throat? Well, you can't do it literally, of course. I can't force them to accept the ideas and allow me to publish and so on, but nevertheless, I had to publish something. So what do? You're back here, disappointed, wondering what to do. Well, we decided to look at what we could do. So we decided to think about, how does this change how we understand not only the problem we had, that is to say, creating a new programming language and doing so with these pattern replacement pairs, but also how does it change how you think about programming and what might we do with that idea? So this, at the time, or any time, is a Pascal program to do a bubble sort. All students at the time were learning this algorithm, and probably every one of you can reproduce it by rote without even thinking about what it means anymore. But it's bloody awkward. It's got a ton of stuff that I have trouble explaining to students and doesn't really tell us much about what's going on without a lot of talk. I could spend a lecture teaching first years about what's going on here. But of course, if we look at it in the this means that way, what it actually says is, for every pair of misordered values, replace it by the ordered pair. And we can say that this, xy, means that, yx, whenever the value of x is greater than the value of y. That's easy to explain. That's easy to understand. That doesn't involve a whole pile of stuff that you have to say to the students, don't look behind the curtain. And indeed, we could do that because with this notation that Charlie had developed for the TXL language, we could write that relatively straightforwardly. Now, TXL doesn't have the world's best syntax and still doesn't. But nevertheless, you can explain this relatively easily. It says replace x, every pair x and y of numbers by yx whenever x is greater than y. So when we think that way, a lot of interesting problems become easier to, or solutions rather, become easier to understand. And it allows you to think about computing, not just compiling or language implementation in another way. And with that in mind, around that time, I met Edsger Dijkstra, and Edsger had this famous quote that we decided to follow. He said, "You should only do what only you can do." And we realized that with this tool that allowed us to express things in a this means that fashion, we could write things in a very small space and have them automatically implemented, that if we were to program them in the traditional Pascal-ish way, were going to be very difficult, both to understand and to get right. But if we did them in this simpler way, we could do things relatively easily. So we started to explore that idea and said, well, if we can't sell this idea, if we can't publish the idea of TXL, maybe we can do things with it that we can publish. We're going to only do what only we can do. So we started doing things like this. This is what you see in the upper left rather, is a notation for objects, classes and objects, based on the Turing syntax, which is a prototype of what eventually became object-oriented Turing. And what we did was we said, okay, well, if we want to understand object-oriented programming and implement it, have a new object-oriented language out of an old language, what we can do is say this means that in this fashion. And so what you see on the bottom right there is actually what that means. In other words, the implementation of classes and objects in the Turing language without classes and objects, in the original Pascal-ish Turing language. I'm not going to try to explain it to you, but it's a relatively simple mapping. It simply says, okay, so if there are objects, then if they're classes rather, then there is a type which contains the data, and there are methods, which are procedures that automatically act on objects or records of that type. And by doing that, we were able to very quickly make a very nice demonstration of object-oriented programming simply by writing the transformation in TXL. And that was publishable. So Eric Promislow, another student of mine at the time, and I published a paper in the same conference about how we could rapidly prototype object-oriented programming using this transformational approach. The paper doesn't talk very much about transformation. It basically talks about it in the way I just showed you as the blue arrow, and talks about how we understood what things meant in that way. So, as Dijkstra observed, we could do things that only we could do at that time and publish the result of that. So that meant we could do all sorts of things. So I took that back to my students and my newer students, and this is Kevin Schneider, who is now at the University of Saskatchewan. He's a former head and dean, and I don't know what his position is right now, actually. Anyway, Kevin realized that one of the things we could do with TXL is we could take source code and we could extract from it, we could extract models of it. So we could actually do what's called design recovery and extract from source code a model which he realized if we made the model in a text language like Prolog facts, for example, we could represent the graphs as text, and then they become this means that pairs in TXL. And with a lot of work, he created a first version of a design recovery system. We weren't even sure it could do it because, as I said, at the time, computers could barely run TXL. And I think his first practical extraction of a model from a large Turing program took about 16 hours on the computer we had at the time. And we weren't even sure it was going to complete because we sort of couldn't follow all the intricate transformations that were going on in the meanwhile. But that one was publishable. We could talk about that. We could say how we did it. We could show you results. Again, without telling you how we did it. Another student of mine, this is Meda Shukla, realized that we could do the opposite, that if we had a representation of a model, we could automatically generate the source code for a system to match that model from the model. This was an early version of model-driven engineering around 1992, I'm going to say. And at the time, we were calling it metaprogramming because the way it worked is that it used templates for source code, and then we would transform facts in the model into sets of facts in the model to instantiations of the templates. And actually, it's kind of interesting because this is a two-level TXL implementation. So the first TXL transformation generates TXL programs that implement the second TXL transformation. So it's a second order transformation problem. But when we published that one, people began to become interested in things we were doing. Around that time, we realized that although Charlie was good at artificial intelligence, he wasn't that great at programming language semantics, and we didn't really understand what our own TXL processor was doing. So we recruited my colleague, Andrew Malton, and Andrew did a very nice denotational semantics. And of course, that's interesting to another community, and we could publish that. So we were doing all right. We were able to do things. I passed on to my doctoral student, Thomas Dean, after his graduation. He started working with TXL. And he realized that we could do very interesting things by, more powerful things, by splitting TXL transformations into sequences of transformations. And by doing that, we actually could use different syntactical views of the programs or the systems we were transforming for the different parts of the transformation. And I'm not going to try to explain all that to you, but again, that's a publishable result, and we did publish it. So we were happily running along, doing what Dijkstra had suggested, doing what only we could do, and publishing all kinds of results without really ever telling anybody what TXL was, because as we discovered early on, that wasn't publishable. No one wanted to believe it. But it was going well, and we were able to publish, and things were going well, and TXL was well on its way to building my career without telling anybody what it was doing. Around this time, I got a call from this man, another winner of a Lifetime Achievement Award from CSCAN. This is Frank Tompa, who at the time was the head of department at the University of Waterloo. And people in industry had been asking him about something called year 2000 problem. And Frank called me up, and he knew a little bit about our work, and being knowledgeable in transformations himself, actually, I'm sure understood what we were really doing with TXL, and thought that maybe we had something to say because we understood how to transform programs about what we could do for year 2000. Now, I hadn't heard of the year 2000 problem, and I had no idea what it was. And at first, I wasn't really sure I understood why he thought we might have something to say about it. So I looked into it and discovered that there were a lot of people in the business community and the government community who are really afraid of this thing. And I'm going to quickly explain to you why they were afraid of it, because it turned out to be more than we thought. So what's going on here is that for centuries, people had been representing in accounting books the year as 2 digits rather than 4. So they would put 99 for 1999 and 97 for 1997, and had been doing so, as I say, for a couple centuries before on paper. And when computer systems were made to do business accounting, they adopted that same convention and used 2 years. And of course, it's no problem, because when any of us reads 2 digits of year, there's no ambiguity for a human being of what it means. And simple computations like this work out very well. So there's 2 years difference between 99 and 97. So to come up with interest, you take the principal, multiply it by the rate and over time, and come up with an interest charge, in this case of $30. The year 2000 problem, of course, is about what goes wrong when you suddenly are 2000 or 2001. So 2001 in a 2-digit year is 01. And if we subtract 97 from that, we get minus 96. We do the computation, and it ends up that the bank owes you $2,880 rather than you owing them $30. And of course, the banks didn't like this idea at all. And they were really afraid of it because the average bank in Canada at the time had about 500 million lines of source code, and they had no idea where the computations that might depend on this were in it. So I saw this problem and I looked at it and I said, wow, Frank, you're right. This looks like a transformation problem. All I have to do is change it to another solution. And I recall saying to Frank at the time, probably one of the stupidest things I've ever said in my life. I said, yeah, using TXL for this year 2000 problem is frankly like using a Ferrari as a lawnmower. It should be absolutely straightforward. Let's do it. And what I was thinking was, okay, if we have computations like this one, I just have to look for them and say this means that. So the fix is I have to do the 4-digit interpretation of the 2-digit years, and presto, it all works. What's the 4-digit interpretation? Well, it's the same one that you and I would use. We figure out what now is. We look at the digits and say, it must be that one. And I can write a function to do that. So, hey, no problem, right? This means that. I write a couple of TXL rules to implement this, and presto, 500 million lines of code is suddenly fixed. Well, no, sadly, it's not exactly like that. The computations in the source code look more like this one. They don't say this year and that year. They don't say it's a year at all. And they have all kinds of funny temporary names like X2 and X1. And if I ran across this computation in a program, how do I know whether that needs to be transformed at all? Well, I don't. I need to know what X2 and X1 are. Are they actually years? Are they 4-digit years? What representation do they have? And then we ran across the further problem that, at least in the Canadian banking system, there are at least 43 different representations of dates. So not only do I need to know that X2 and X1 are dates, but I need to know which one of the 43 possible representations of dates they are in order to do anything about fixing them. So the problem becomes much, much more difficult. Fortunately, we understood how to do design recovery. We understood how to make a relationship, an entity relationship model out of a program, more or less automatically using TXL. So we could generate a model that said, okay, the thing called this year is related to the thing called X1, possibly by a comparison or by an assignment or by some other operation in the language. And we know X1 is related to X2 because the one's subtracted from the other in this particular statement. So what we can do is we can say, okay, if I know that one of the things has a representation, I know it's a date, the thing called this year. Maybe I know because of its name, or maybe I know from other evidence. It was assigned 1995 or something. And maybe I know its representation because I can see how it was declared. If it's related to X1 and X1's related to X2, well, then this means that. In other words, I can infer that X1 is also a date and that its representation is probably YY, depending on what that relationship arrow is. And X2 then also has that characteristic. So yes, we can do that using the this means that source transformation TXL style as well. And that's what we did. We created a system with about 30, I think, or 40 TXL transformations in it to do design recovery on COBOL, PL1, and RPG programs, to create a fact base, to identify from that fact base hotspots, we called them, in the source code, so places where dates are manipulated, and to do an analysis of that fact base to infer ones that we didn't know, and then finally to transform the source code to fix the Y2K problems. Spun off a company to do that called Legasis, or DRI Legasis, and sold a license for our transformational solution to IBM Global Services, and in the end, hundreds of billions of lines of code. Well, no, I'm wrong. Tens of billions of lines of code ended up being automatically analyzed and transformed for the year 2000. And when the year 2000 came, the Canadian banking system, at least, didn't run into many major problems. Even better, even better, when we were done with this, we could publish those results. We could publish what we had done and how we had done it, and my academic career could continue. About this time, after the year 2000, a lot of people in computing began to realize that this idea of transformation, of source transformation, source code analysis, this means that transformation in source code for programs was interesting. The year 2000 problem proved that. We were not the only ones using that kind of solution. And so out of the blue one day, I got an invitation to a brand new workshop on source code analysis and manipulation. And I looked at that and I said, aha, this is the conference for TXL. They've invented the TXL conference. That's Mark Harmon down in the corner, who at the time was at Brunel University, rather, and is now at Facebook, actually. Anyway, Mark, you'll notice, was not only a visionary in creating this new area conference and observing that transformation and source code transformation and analysis was interesting, but he was a bit of a fun guy, and he called this conference Scam. And he held the first version of this conference in Florence, in Italy. So you can imagine trying to explain to your dean that you had been invited and had a paper accepted at a scam in Florence. Well, yeah, that was a challenge, but nevertheless, we went to the scam in Florence, and it was indeed the place for us finally to talk about TXL as what it was. And we created a a paper about our experience and introduced TXL itself for the first time explicitly in the paper at that workshop. And yeah, it went very well. Finally, the world was ready for it. After that time, in the next decade, we continued exploring all the things you might do with source transformation, with the this means that idea. And among other things, we created a very novel clone analyzer, NiCad, which has become extremely successful in its own right. We did security analysis and correctness analyses of programs. We used TXL to analyze laws and regulations written in English and Italian and extract from them software specifications for keeping software consistent with the law. We worked on artificial intelligence and pattern matching problems like analysis of handwritten mathematics using TXL transformations. By the way, in these pictures, every one of those blue arrows is a TXL, this means that arrow. And we developed an analyzer for model-driven engineering systems, in particular in the Simulink modeling language at General Motors and other industrial places. And of course, each one of these projects was led by one of my spectacular doctoral students, who these four are representative of. There are many others, and even many others involved in these projects. And Chanchal Roy and Richard Zanibi and Nadia Kievitskaya and Manar Alalfi all worked on these things, and they worked in the way that Rick Holt had predicted. I pointed them in a good direction, and I get to take credit for where they went with it. So we were happily continuing on our path using TXL and creating all kinds of new things, doing what only we could do and publishing lots of papers about these things. And then finally, I began getting emails like these. We'd like to invite you to present your TXL research, and so on. Why? Because finally, people were asking, how in the world are they doing these things? And they wanted to know how we did all that stuff. So they began finally, 20 years after telling us that we couldn't publish it because it was impossible, I began to get invited to talk about it. And finally, we could write the paper, which was about TXL and what it does and how it does it. That paper did really well. It became the most cited paper in Science of Computer Programming over a 5-year period. And I think it's still among the top few papers ever in that journal. So the world eventually was ready for us, ready for TXL. After that paper, lots of other people discovered what you could do with TXL. And since that time, in the following decade, hundreds of other research results have been done using TXL, not only by our group, but by many, many people all over the world. So much so that last year, at the, I guess, 19th anniversary of the scam, now it's a conference, we received the 20-year Most Influential Paper Award for that conference for our TXL work. And we were very proud to do that. So this is where we began. This is the man who said, why are you wasting your time on these old ideas? This is Gerhard Goss. Sadly, a few months ago, we lost Gerhard. He passed on in his 80s, and I miss him greatly. But he had another important thing that he would always say. At the end of every IFIP Working Group 2.4 meeting, right up until last year, when I last saw him, he would always say at the end of a talk or at the end of a meeting, so what have we learned? Or rather, so what have we learned? Well, let's look at it. What did we learn from the story? Well, if you have a good idea and it gets rejected or not accepted or people are not happy with it, it doesn't mean it's not a good idea. It might mean it's a really good idea. And so what can you do about that? Well, if the idea itself can't be accepted, if it's a good idea, if it's an idea that might have impact, then you have an enabler. You have something you can do that others can't do because they don't yet understand it or aren't willing to. So you can carry on in that way. And if you do so, you can be successful in a research career. You can do all sorts of things and you can carry on. And if you're lucky, someday people will notice. And when they notice, you'll be ready. When they suddenly think your idea of all those years ago is a good idea and interesting, you'll be ready and you'll have lots of examples. And that's what happened to us. That's where my career came from. So, what's the moral of the story? Well, the moral of the story is, if you stick with a good idea long enough, eventually, maybe, someday, this means that. All right. So I'd like to thank you and to point out that, exactly as Rick predicted, the secret to research success is pointing your students in a good direction and staying out of the way. And by God, I have had to do an awful lot of staying out of the way. And these are some of the people whose way I stayed out of. Thanks very much.
Thank you, Jim. And congratulations on your Lifetime Achievement Award. You're quite right. We have some wonderful, accomplished computer science pioneers, and now you get to be one of them who've won the award. I want to read you a couple of the comments here. You can probably see them. What Carrie Williamson says, what a great example of a storytelling talk. Audrey Girard says, congratulations, Jim, well-deserved and a great talk. Gazelle Fard says, what a wonderful presentation. So proud of you, Dr. Cordy. If there are any questions, you can either raise your hand and I'll try to get you to say it. I'm going to try this technology. Otherwise, put it in the chat. And we have a few minutes left before the end of the webinar, and we can use them to have Jim answer some questions. Otherwise, the kudos are coming in, Jim. Amazing talk. Thank you very much.
Well,
Off to do what only I can do. You've motivated some people. I was going to write that one down and put it up on my desk.
Yes, that's what I want to see. Get out there and do what only you can do.
It's quite motivating.
Well, the other thing is that if that I didn't say maybe completely clearly is that was a really simple idea. The idea we started with was spectacularly simple. And another, I didn't show other reviews of it, but another review we commonly got was, yeah, this is a really simple idea, so what? And you have to watch out because the best ideas are definitely the ones that make the world simpler, not the ones that make it more complex. And so when you have something that looks simple, you have to remember that before you proposed it or understood it, it wasn't simple. It's the achieving the simplicity that is the contribution and that will make the difference.
Hassam I've allowed you to talk, Hassam, if you'd like to, at least that's the theory, had a question.
Hassam, you're muted.
Yeah, I think you have to unmute yourself. Allow to talk. That this doesn't seem to be working, and I apologize. Perhaps you could type in the question. But you definitely inspired a lot of people, and for that we thank you. Excellent presentation, very inspiring. And this is exactly what we wanted to have our award winners be able to do, instead of necessarily talking about your research in general, but to inspire people on your journey and how they could learn from it. So thank you very much, Jim. Thanks to everyone who participated in today's talk. We will have the slides and the recording up on our website sometime next week, and look for the next presentation, which will be in November around the Canadian Women in Computing Conference. So we're working on that right now, and we'll put that out to our membership in the next couple of weeks. Thanks again, Jim. Everyone take care, stay healthy, stay safe, and we'll see each other at our next webinar. Thanks.
Thank you, Adele, and thank you, everyone. It's
Take
been
care.
fun.
Bye-bye.